Surprisingly, the material we study here doesn't involve you learning any new syntax. You already know everything you need to know in order to study recursion. We're going to be writing methods like we've written before, but instead of having one method call another method, sometimes that method will be calling itself. It seems like a strange thing, but it gives us an awful lot of computational power. So for example, we've seen that the distance between 2 points may require calling the square root method. That's one method calling another. Here we're going to use multiplication and addition in a recursive kind of way, which is a pedagogical example, but we can illustrate how recursive methods work. So these methods call themselves. It seems almost impossible to solve a problem P by calling P when you haven't even finished writing P yet. But it works under the right circumstances, and it's a very powerful technique. So why study recursion? It turns out you could live without knowing recursion. You could compute everything that's computable and never write a single recursive method. But it's a very powerful way to look at computation. The resulting programs tend to be very elegant and very concise. But if you have arrays, iteration, and choice, the material you've studied so far, you actually know enough from a theoretical point of view to solve any problem that can be solved on a computer. But understanding recursion will give you yet another tool in your ability to solve problems, and you'll find it a very rich and powerful technique. Nature itself gives us many examples of recursion. If you go out and look at a tree, if you look at the tree very carefully, all of the branches of the tree seem to reenact the same pattern. It's as if nature's being very economical and just giving a tree one way to grow itself. So it splits here, but each of those splits further splits. And each of those splits, if you look at the tree, are very, very similar. Unless some trauma has happened to the tree, you'll see the same pattern occurring recurrently. The shapes that we might study, such as the ones you see here, are also recursive shapes. We can draw things like snowflakes, interesting triangles, articulated triangles. Almost any shape like this can be specified in a recursive manner. Recursion often seems to do the impossible. Here you see a stack of mirrors that apparently goes on forever just by having an orange frame mirror opposite a black frame mirror. So looking into the mirrors, it appears to go on forever, and for us that's not going to be computationally feasible. Our mirrors have to stop at some point and compute some result on the way back. Escher also is very famous for drawing recursive figures. Here you see one hand drawing another, which would be impossible from a three-dimensional point of view, but in 2 dimensions it looks just fine. So we'll begin our study by looking at various kinds of formulas that can be looked at recursively, and we'll be studying how to find recursive substructure in these formulas.